Good day, I'm Norman Wildberger. Today we're going to introduce a very important notion in modern analysis, the idea of a limit. And not surprisingly, we have a somewhat different take on limit than in most treatments. I think that even if you're a professional mathematician, there may be something in this video that's new for you. So let's start out by just an intuitive understanding. Here's a sequence: 1, 1/2, 1/4, 1/8, 1/16. We intuitively feel that the numbers are getting smaller and they are approaching, in some sense, 0. So we might say that the limit of the sequence looks like it's tending towards 0. Here's another sequence of terms getting smaller: 1, 1/2, 1/3, 1/4, 1/5, approaching again 0. At least it looks like it. This is a different kind of situation where we have numbers 0 and then 1/2 and then 3/4, 7/8, 15/16. Now it appears as if the numbers are approaching 1. So in each case it appears that the sequence of numbers on the left approaches the number on the right, if you keep going. Of course, there's some difficulties with this because on the left-hand side, the sequences are not really well defined. Just specifying a few terms doesn't, of course, lay out the full sequence. And more importantly, the notion of a sequence itself is highly problematic. We have not defined the notion of a general sequence. In fact, we've been rather careful to restrict ourselves to rather specific so-called on sequences associated with polynomials or polynumbers and rational functions or rational polynumbers. In any case, the idea of becoming clear about what approaching a limit means is a 19th century development. And I guess most of the credit goes to a great French mathematician, Cauchy, who I guess asked the question, what does it exactly mean for a sequence to approach a limit? And the answer that he gave, and that was further developed by others, became a cornerstone for modern analysis, the notion of a limit. Cauchy, and then later Karl Weierstrass, formalized the so-called epsilon delta definition of a limit, at least according to the usual story. And this is a rather technical formulation of what it means for a sequence to approach a limit. For example, the limit of the sequence S of n as n approaches infinity equals a. Or alternatively, a slightly different context, the limit of a function f of x as x approaches a equals L. So in both of these cases, the idea of what these things mean was encoded in a certain logical structure involving two arbitrary, generally small numbers, epsilon and delta. So generally referred to as the epsilon delta approach to limits. Unfortunately, this theory does not really work. Okay? There's serious logical gaps, not surprisingly, with the current modern treatment, the epsilon delta treatment of limits. Even though, ironically, this is perceived by the Academy to be some kind of high point of rigor, and it's perceived to be a particularly insightful and carefully laid out definition. But in fact, when you look more carefully, you see that it is not exactly so. So most calculus texts are wrong when it comes to the notion of limit. In fact, the notion of limit that's usually given is not only problematic logically, but it's also rather difficult for students to, first of all, get their heads around abstractly, and secondly, actually to practically work with. So the reality is that most calculus students, even at the university level, are only told about the epsilon delta definition of a limit, but not actually seriously presented with it. It's deemed too hard for most undergraduates to understand. Nevertheless, although there are things wrong with it, the basic idea nevertheless has merit. There are underlying the technicalities some very good, solid ideas that can be reformulated without too much work to make them more solid. And that's the kind of job that we're interested in doing, of course. So at the risk of sending you all scurrying in different directions, here is the official epsilon delta definition for the idea of the limit of a sequence. Let's have a look at it at least. Let's lay it out on the open so we can at least get an initial orientation to what this means. But I warn you that this is a difficult notion, and rightly so, because there's actually some ambiguities logically in it. But we would like to at least get a sense of what's going on with it. All right, so here's a standard definition of the limit of a sequence. Let's call the sequence S of n. And I'm adopting the usual calculus point of view to these things, where one doesn't actually need to define the word sequence. It's just bestowed upon us as our birthright that we happen to know what that word means. All right, so we have a sequence S of n. N is a natural number, so we're thinking of S of 1, S of 2, S of 3, and so on. And what we want to do is define this expression here, what it means for the limit as n approaches infinity of S of n to be a, where a is some fixed number. What does that mean? So here's the definition, essentially going back to Cauchy and Weierstrass. It means that for every epsilon greater than 0, there is a natural number n, capital N, such that this holds. What is this? This is the implication that if little n is bigger than or equal to capital N, then the absolute value between S of n and a, in other words, this difference in absolute value, is less than epsilon. So it's no surprise that this is a very intimidating definition. Okay? Do not be worried if this sounds like a whole bunch of gobbledygook if you have never seen it before. It's a difficult definition. And in fact, we're not going to adopt this definition, so it's not going to be too important for us that we completely understand it. But nevertheless, I want to give you an initial orientation to what it means. A picture. So we're going to imagine the sequence S of n laid out in this way. This is recording the sequence. Here is the value S of 1 above the x-axis. So in this case, S of 1 is perhaps 1. And here S of 2 is perhaps 2. And S of 3 looks like it's 4.5. And S of 4 is maybe 5. And S of 5 is maybe 5.5. Okay? So for every natural number, n, we have a possibly rational or possibly real number value, according to the modern mathematicians, S of n. And that's indicated by these points here that are a graph, actually this one too, that are a graph of this sequence S of n. Now, what about this number a? Where does that figure? Well, that is some number which you can think of as being a place on the vertical axis. In this case, 1, 2, 3, 4, 5. Looks like a is 5. And here's the value 5. That green line represents the value 5. And we're interested in the sequence approaching 5. The limit of the sequence is this value a. The idea that as we keep going further and further and further along, these values start getting closer and closer to 5. In other words, they start getting closer and closer to the green line. Right here, they're bouncing around, sometimes close to the green line, sometimes further away. But the idea is that as we keep going, they should start getting closer and closer to the green line if the limit of the sequence is a, which is 5. Okay, so how do we capture that idea? So the idea is that for every epsilon greater than 0, and you should think of epsilon as being a little displacement from a. So epsilon in this case is actually 1, what I've pictured. So we imagine a little interval centered at a, epsilon in this direction, epsilon in this direction. And that interval is then registered by these red lines. All right, so the numbers that are within epsilon of A, or whose y component is within epsilon of A, are the numbers in this red band around the green line. So the condition here says that for every epsilon greater than 0, so for example for epsilon equals 1, there should be some position or some natural number capital N such that if the little n is bigger than capital N, in other words, if we're to the right of this fixed position, then the difference between S and A is always less than epsilon. In other words, from this position on, the sequence is always in the red band around the value A. And in this example, we can kind of see that partially happening. The sequence is sometimes in and sometimes out of the red band up to this value of n, which I suppose is equal to 10. And then from then on, it looks like it might be the case that all the sequence's values from then on are in the red band. Even if we go very, very far in that direction, they're always within 1 of 5. All right, so given epsilon, which is 1, there's a natural number n, so that if we look at little n past that point, then the difference between S of n and A is always less than epsilon. Now this condition has to be satisfied not just for epsilon equals 1, which is what I've shown you here, but it has to be satisfied for every epsilon. So for epsilon equal to half, for example. If epsilon was equal to a half, then we would have to change this picture by moving these red lines closer to the green line. So we would compress the interval around A. So just a half on either side. So imagine a sort of smaller band or tighter band. Then we would require that there's some new number, capital N, so that if we're past that new number, that from then on, all the elements in the sequence would be in this smaller band with separation a half from A on both sides for all elements in the sequence past this other n. So the requirement is, let's summarize, that the limit of the sequence S of n is equal to A as n approaches infinity if for every epsilon greater than 0, for no matter what small interval we take, there is some position, capital N, so that beyond that position, so when n is bigger than that fixed position, then we guarantee that the difference between the sequence's values and the limiting value is less than epsilon. It's a major definition. It's not so easy to understand. It's also not entirely so easy to work with practically either. There's a slight departure that I've introduced when I'm writing it this way. I've written it with brackets here. These brackets are not usual. Without the brackets, it seems to me there is a real possibility of confusion as to what the logical structure of this right-hand side is. It's very easy then to get confused and think, well, this implication might refer to if all of this is true, then this is true. But it's not like that. It's for every epsilon greater than 0, there is a natural number such that this whole condition is satisfied. All right, so why is this problematic? It's problematic for a number of reasons, which are what? First of all, we have not defined what a sequence is. So the very objects that we're investigating here have not been properly defined. That is, in fact, a very serious problem. The second is that in the modern treatments of things, the numbers that are involved, the epsilon, the A, the sequence values, are allowed to be so-called real numbers. And as I've mentioned many times, up till now, real numbers are an optical illusion. They do not really exist. So the whole setup with real numbers is a distortion of what it really ought to be. And it's ironic too that although this definition of limit assumes you already know what real numbers are, in fact when you go to a lot of places and find out, well, what actually is a real number, you find that real numbers are defined in terms of limits. So somehow there often is a kind of circularity floating around underneath the carpet if you bother to look. There's another issue. Well, we haven't talked too much about absolute values. The absolute values are all right, but they're just a little bit problematic, but it's not too serious. But there's something more fundamentally problematic about this definition, which is what? So the nature of the right-hand side is in some sense open-ended. In other words, it does not make very clear what actually is required to prove that the limit of S of n equals a. Okay, there's this condition that for every epsilon greater than 0 there's a natural number n satisfying a certain condition. But what do we actually have to check? Are we obliged to go through all the possible epsilons and for every possible epsilon compute an n? So I've shown you, for this sequence, and maybe if epsilon is 1, then maybe n is equal to 10. And maybe if epsilon is a half, we can work out that n has to be 20. And maybe if epsilon is 1/10, maybe n has to be 100. And if n is 1/millionth, then maybe n has to be 10 trillion. So we can keep going, choosing different epsilons. For each epsilon, we can work out an n. But this condition requires us to simultaneously do that for all epsilons. And what does that mean? How does one check this condition for all epsilons? Well, if you're a novice to this, you probably don't know what to do. But if you've seen some examples, then what you will see is that what's usually done in this situation is to find a general argument, to find a general formula that allows you to go from a general epsilon to a general formula for n in terms of epsilon. So what's really required to verify this is not a number or a bunch of numbers or anything too specific. It's actually a formula. A formula that tells us how to go from epsilon to n. So if you were writing a computer program to try to check whether someone's solution or proof of a limit actually worked, you'd have a very hard time. Because it's not so easy to check whether a given formulation of this relation between epsilon and n is a valid one. So logically speaking, there is, I think, a very subtle ambiguity as to what exactly the definition really requires. It's a difficult definition. Students struggle with it, and mostly, in most calculus courses, this is slid under the carpet, this limiting definition, and people are just told, well, believe us, there is a definition that officially works, but you don't have to really worry about it unless you're becoming a professional mathematician. That's clearly not a very adequate state of affairs. So let me just record some of my concerns with the definition of a limit. The term sequence, first of all, is not defined. That's a clear problem. The usual usage assumes that these objects are so-called real numbers, and real numbers are never properly defined. There is a fix for this problem. The fix is just to use rational numbers, and that can be done. So this is not insurmountable. Another issue is, how does one verify that for every epsilon greater than 0 there is an n in natural numbers, etc.? What does this actually mean? What is actually being asked here, specifically? For example, do we need to actually prove this association between epsilon and n, or do we just need to somehow state it? And there's an issue about absolute values. So again, here this little table is illustrating the conundrum associated to these points, that for every epsilon there's supposed to be an n. Epsilon equals 1, maybe n is 10. Epsilon is a half, maybe n is 37. Epsilon equals 5, then maybe n only has to equal 1. But are we obliged to fill out this table? It's clearly impossible for us to fill out the table for all values of epsilon, so what exactly is the definition requiring? It's requiring some kind of abstract statement or proof, but the nature of that proof or theorem is not very clearly enunciated, I think, in the definition. And then there's the issue of whether the absolute values are really needed. That's a little bit more important when we go to higher dimensions. That issue rears its head in higher dimensions a little bit more than it does here. All right, so I would like to propose an alternate way of thinking about what a limit is. And my approach is to start simple. So we're going to work in the context of rational polynumber on sequences. And what that means is rational polynumber is just our name for what's usually called a rational function. And an on sequence is just our word for a sequence that keeps on going. An infinite sequence, so to speak. So we're only going to be looking at those sequences which are given by rational functions or rational polynumbers. So it's a relatively restricted class. But so far, those are the only ones that we've been able to define in a very consistent and completely clear way. So we're going to stick with those for now. So for example, here's an example of a rational polynumber, or usually called a rational function. So 4 plus 2 alpha plus 3 alpha squared, that's an integral polynumber. And here's another integral polynumber, 1 minus 3 alpha plus alpha cubed in the denominator. And this formal ratio is a rational polynumber. And associated to it is an infinite sequence, or on sequence, meaning just a sequence that keeps on going. This is how we write the sequence, by replacing the alpha with an n. Little n is our favorite letter for talking about sequences. And we can generate actual values for the sequence by successively replacing n with 1, and then with 2, and then with 3, and so on, as far as we have patience with. That's the associated on sequence. So our aim now is to define what we mean when we say that the limit, as n approaches infinity, of p of n equals a. So a here is a number for us, which is a rational number. P is a rational polynumber like this one here. And we want to know, what does this mean for us? What does it mean when we claim that this on sequence is heading towards some particular value? How do we express that idea concretely and precisely? Well, whatever our definition is, it had better have the following properties. It had better be the case that if we take the limit of the constant sequence, say the constant sequence 2, that the limit as n approaches infinity of this sequence 2 is itself 2. Reflecting the obvious fact that the sequence 2, 2, 2, 2, 2, 2, and so on, that its limit is 2. Another very important thing that we're going to need is that the basic sequence 1 over n, sequence 1, 1/2, 1/3, 1/4, and so on, its limit had better be 0. And that's our fundamental example of a sequence which is converging to 0. So if that's not converging to 0, then nothing else is. And here's a slight variant when we take 1 over n squared. So the sequence 1 over 1, 1 over 4, 1 over 9, 1 over 16. This is also converging to 0. So its limit should also be 0. In fact, if we replace the n squared here with n cubed, well, then we also get another sequence that converges to 0. And finally, the sequence n, the limit as n approaches infinity of n, namely this sequence here, the sequence of natural numbers themselves, 1, 2, 3, 4, then its limit if it exists at all, had better be infinity. So if we want to talk about the limit of this sequence, we're probably going to have to introduce some kind of extension of the rational numbers, like the extended rational numbers we've been talking about. And in that case, it might be perfectly reasonable for us to say, yes, the limit of this sequence is infinity. So these are some guiding examples that we certainly want to have true if we're going to define this notion of limit. Okay, so here's our definition. If P of n is a rational polynumber on sequence, so P is a rational polynumber, and this is the sequence associated to it, and A is a rational number, then the limit as n approaches infinity of P of n equals A precisely when the following. So this is the condition that encapsulates this limit. So what is the condition? The condition is that we can find k and m natural numbers so that if n is bigger than or equal to m, then the difference between P of n and A is sandwiched between k over n and minus k over n. So the limit as n approaches infinity of P of n equals A precisely when we can find k and m so that this condition is satisfied whenever n is bigger than m. What's the meaning? The meaning is that the difference between P of n and A should be getting small as n gets big. And it's getting small in a way that's sandwiched between k over n and minus k over n. This is a small positive number. This is the small negative number, the negative of that one. This difference here has to be sandwiched between the small positive number and the small negative number, so it's getting close to zero. That's what this is telling us. And the bigger n gets, the closer these two things are to each other. The tighter the sandwich between this thing and this thing, meaning this thing here has to get closer and closer to zero because it's between some number and it's negative. What is k? K is just a scale that allows us to have some flexibility to fit the difference between these things to the n. So these two numbers are important, m and k, in this definition. I'm going to give them some names. So we're going to say that m is the start and k is the scale. So these, we'll also refer to them as certificates for the limit. So the idea is that if you want to prove that a certain sequence has a certain limit, what you're obliged to, by this definition, is to find two things. You have to find a natural number k, called the scale, and a natural number m, called the start. So you have to exhibit k, you have to exhibit m, and they're natural numbers like 7 or 23 or 3,492. You have to show us what k is, show us what m is, and k and m have to have this property that whenever n is bigger than the m you've chosen, the start, then this inequality is satisfied, sandwiching the difference between P of n and A between k over n and its negative. This is very different from the classical definition. In the classical definition, we're asked to start with an epsilon and find a capital N so that some condition is satisfied. Here it's somewhat different. We're asked to find two numbers k and m, and present you with the two numbers k and m, which make this sandwiching work. So we can think of these k's and m's as somehow certificates for the limit. They are documents that guarantee that the limit works, so that you can verify that the limit actually works for the certificates that have been chosen. So let's see how it works in practice. Always the litmus test. So let's start with the simplest example. A constant sequence. say the constant sequence 2. Is the limit as n approaches infinity of 2 equal to 2? We have to check the definition. So here's this constant rational polynumber that we're thinking about, p equals 2. And what we need to do is we need to find a natural number m, called the start, and another natural number k, called the scale, so that if n happens to be bigger than m, bigger than or equal to m, then the difference between the sequence and its limit is between k over n and minus k over n. But wait a minute, the difference between the sequence and its limit is always 0. And 0 is always between this positive number and its negative, no matter what k and n are, as long as they're natural numbers. So this holds for any k and n natural numbers. That means there's no obligation on us to choose particular m or k. It means we can choose any m and any k that we want, and we prefer to choose a smaller m. So let's choose m equals 1 and smaller k equals 1. And then if n is bigger than or equal to m, which is 1, then indeed this difference 0 is between 1 over n and minus 1 over n, the k being 1. So note that the m and the k were not unique. In fact, in this case, any m and k natural numbers would work, because this is a very simple example. And let's look at the second example. The limit of the sequence 1 over n as n goes to infinity. We want to show that that's equal to 0. So we have to check the conditions for the limit. So our rational polynumber is the 1 over alpha. And what we need to do is to find a number m, called the start, and a number k, called the scale, both natural numbers, so that what? So that if n is bigger than or equal to m, then the difference between the sequence and the limit will be sandwiched between k over n and minus k over n. So we want to find m and k so that this inequality holds for all n bigger than m, bigger than or equal to m. So we look at this inequality. What is it actually saying? Well, the 1 over n minus 0, that's just 1 over n. And we can see that that's going to be a valid inequality if we just choose k to be equal to 1. So if we choose k equal to 1, then we can choose m equals to 1 because it's going to hold for all n. So if n is bigger than or equal to 1, or m, then minus 1 over n is less than or equal to 1 over n is less than or equal to 1 over n. This is a true inequality. And it's the inequality that we want to have satisfied if k is equal to 1. So we found the m, we found the k, they're both equal to 1. Those are certificates that we can present that demonstrate to us that we have satisfied the crucial inequality. We have bounded the difference between the sequence and its limit between a multiple of 1 over n and the negative of that multiple of 1 over n. Okay, these are all still baby cases, so probably you'd like to have some challenges and try some slightly harder examples. So here's an exercise for you to show that the limit as n approaches infinity of 1 over n plus 1 is also 0. That the limit as n approaches infinity of 1 over n squared is 0. And a little bit trickier, the limit as n approaches infinity of 1 plus n over 2 plus n is 1. All right, so great little exercises for you to practice your logical skills, and maybe also a little bit of manipulation with inequalities. We haven't said very much about inequalities, but to carry on with a discussion of limits, we need to say a little bit more about inequalities to remind you of how to manipulate them a little bit. So next time we're going to have a look at that. So we're going to look at some more examples of limits in this somewhat new and better way. And we're going to apply inequalities to be able to tackle slightly more sophisticated limits. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.